Hey, welcome back. You might remember recently I did a video on a threading insert that I modified to turn a PG 13.5 Panzerrohrgewinde, which is a bit of an oddball thread. And I mentioned that the thread goes onto parts that screw into a bioreactor. And this is going to be the video on making these filler ports or insertion ports for the bioreactor. The customer supplied me at the time with a rough sketch and I put it into CAD, and this is what we agreed on. We have the PG thread here, we have a hex section here so you can tighten it down with a wrench. These two surfaces seal with an O-ring against the bioreactor. So we have a radius so you can roll the O-ring over this edge without damaging it. We have a 45-degree cut on the end, so when this hangs down into the bioreactor and the liquid media that goes through it has a defined point where it forms droplets and drops off into the reactor. And that seems to be standard for something like this. Also, we have a cutout feature back here for there is a silicone hose or something similar that gets pushed over it and then secured with a hose clamp or a zip tie. Seems to be standard too. 6mm through hole all the way through the part. So let's go in the shop and make the actual part. Material is 14404, otherwise known as 316L, also known as V4A. Versuchsschmelze austenitisch Versuch 4. I already did the first one off camera just to show you what we're going to make on the first operation. We start from solid bar, obviously. And we turn the small diameter, this a step, and then the PG 13.5 thread, which are with our gauge ring as a as a gauge, obviously. And then we part it off, I bandsawed it off because I don't have a parting tool for this diameter that works particularly well in the stainless steel. So bandsaw it is. Also, I drilled it 5.8 millimeters, a little bit over half the length of the part. I'm going to drill from the other side too. Then I'm running a reamer through the entire length of the part, and the reamer will hopefully clean up the entire inside and also kind of squeeze out any misalignment or drift of the drill. I don't expect terrible amount of drift on the drill, but there is most likely a little bit since it's about 8 times diameter to go to half of the length of the part. Everything else is kind of basic on it, nothing special. Small radius here, and overall just a decent surface finish so we don't get problems later when the customer wants to sterilize and clean those parts. 22mm bar, 60mm stick out, and I'm running a CNMG size 09 insert, which is a negative tool holder, but the insert has a positive geometry, so it's a relatively free cutting insert. And now we're just roughing down the overall contour of the part. But I will use the same insert since it's cutting very, very well, used for finishing. That was all the roughing. And now I wait until it's cooled down, then I take my finishing passes. I'm using the same insert style for roughing and finishing here, because on such a light duty machine you do not really benefit from a proper roughing insert. But I changed to a insert that I only use for finishing cuts, and I use this one for roughing cuts. So this has all burnt up edges, and this is very nice. And when I rough the next part, I'm indexing back to the roughing insert for roughing, and then go back to finishing insert for finishing. Okay, next I'm finishing larger diameter to 12 millimeters. Now I need a relief cut in here for the thread. So I'm using a full profile radius insert for a parting tool here, and I figured this will make for a nice thread relief back here. So tool number 20. Touching off on the face here with the insert, careful not to chip it. Moving over the width of the thread, 8 millimeters. Dropping the speed. And plunging in. Idiot checking. Yep. Ugh. Aww. Oh, this tool just does not want to behave. This insert is just terrible. I just freehand touched it up and I did an awful job. But running the VFD on this machine, I can play with the RPM while I do a plunge cut, and that kind of makes it behave. It's not pretty, but I'm only making 3 parts here, so I don't want to make a science fair project out of it. Chamfer tool. This tool, on the other hand, behaves excellent. A little bit of cutting oil and you can just plunge a 1mm wide chamfer without any trouble. Despite being a 0-degree top rake or a neutral top rake. Okay. Now we do our threading on here. With the insert that we just ground. I would prefer not to chip it. And some cutting oil. You have to be extremely careful with thread gauges on stainless steel. It's so easy to permanently seize them on the part, especially if there is a burr or if you have, for example, very fine debris in your thread gauge. This will result in some terrible problems if you're not super careful. I'm taking one last spring pass at an extremely low speed just to make kind of a scraping pass on the thread. Okay, it made a terrible noise but left a nice finish. Threading usually throws up a little bit of burr on the end of the thread. Here you can see the burr that got rolled over by the threading tool into the starting chamfer. So using the chamfering tool to clean that up. And the same on the back side. This happens because the thread angle and the chamfer angle are different. So there is space for a burr to roll over. And we just use the super sharp chamfering tool to trim the burr away. Keep in mind this is before deburring the thread. Now the thread gauge is very tight on here, but free moving. Next I will do my thread deburring routine that I always do if I don't have a topping insert that cuts the top of the threads. I use a fine needle file and I just hold it like this, let it run through the thread, and then I hold it like this and let it run through the thread, just to break the top edge. After the file, we have of course our trusty piece of rubber abrasive. You want the thread to be in a condition where you can run your fingers along it, like along the thread crosswise and every direction, without cutting yourself. You don't want it to be completely undefined and mushed over. You want it to be very nicely deburred. And now if I go with my thread gauge on here, yeah, that feels very much like I wanted it. I'm using a corner rounding end mill that's held in the tool post of the lathe, with one of the flutes aligned as a lathe tool to be horizontal with the world and on center height to round over the corner on the part. Time to drill through the part, starting with a spotting drill here. Like any civilized person, I'm drilling, of course, with carriage, not with tailstock. I'm pre-drilling with a 3.5mm drill, and then I follow up with a 5.8, which is the reamer, pre-reamer drill for a 6H7 reamer. Yes, you can absolutely drill such a deep hole with the tailstock, but that's highly annoying because you can only pack so deep when you drill very deep holes before the chips pack up and want to break your drill or seize it up. Same for opening up the bore. We end up with this bird's nest of chips, and as long as they come out of the flutes, it's fine, but the second they stop coming out the flutes, you want to retract the drill and clear the chips. Preferably you do that before the chips start to pack up, because then the drill will have a tendency to walk off to one side. Okay, that's full drill depth. Quick deburr. Just the tiniest of chamfer. We are reaming from the other side anyways, and also later we cut a 45 onto the end of this pipe section. But I just want an inside chamfer here so I don't cut myself on the burr or disturb my length measurements. I'm just going to use some 3M lapping film, run it over this section, and give everything a very good rub with Kratex. With the Cratex you really can come in and polish and remove any micro burrs and even out any tool marks that are left and leave a spectacular finish. Especially on something like a thread where there might be a micro burr interfering with the other part, it can be really advantageous. Spraying on some isopropane alcohol and blowing the part off to get rid of any abrasive dust. And then we're over at the bandsaw chopping the part off the bar. I didn't have a suitable parting tool for 22mm stainless, so bandsaw it was. I need to cut the parts to 83mm overall length before I proceed on with machining the second side. And I was asked that in the past how I cut parts on a lathe once they are sawn off or parted off, how I cut them to length. Well, it's fairly easy. You put them in a chuck, you face it, you measure it, you rechuck it, and then you cut it to final length. There are not many good other ways to do it. You can get around, if you have to do multiples, using a backstop, especially with a chuck. A backstop works very well with 5C collets, where the collet stop is part of the collet. It's problematic if you're not using a dead length system, because the collet pulls in and your C position of the part in the collet is not very defined that way. Well, the position of the part in the collet is very defined, but the position of the collet in the collet seat is not. That's why the dead length system exists. So for the most part, if I do only a few parts, I'm taking facing cut, measure, rechuck, retouch off, and cut it to length. And I changed to the 6 jaw chuck because I'm clamping on a non-nominal diameter. It's the diameter here is 21.5, and I don't have a 5C collet for that, so I'm using 6 jaw chuck here. So I took a facing cut, and I'm using calipers to measure the overall length. It's 84.17. Part goes back in the chuck. This is also a place where you could use a backstop, but I don't bother. Now I just scratch with the part against the surface again to pick up my 0, enter 84.17 into the DRO, and then I take facing cuts until I hit 83. Took my facing cuts and I can check my overall length. Should be within relatively close tolerance. Comes out at 83 with calipers, so that's perfectly fine. So for the second side of the part, we still use the 6 jaw chuck because, as I said, I do not have a good other way to clamp on a non-nominal diameter. It's 21.5, but I do only have full millimeter step 5C collets. But the 6 jaw is a very nice chuck, so I'm using that. Well, I use it for everything. Get an indicator in here quickly. That's fine from a run-out standpoint. Now with the part to final length, I can use this face as a reference for all dimensions on the second side. So it means picking up my 0, I can either do that with the spindle not moving, just by bumping the tool extremely careful against the face of the part, zeroing out the DRO, or doing it while the spindle is turning. I would say the safer method is to do it while the spindle is turning if you're not 100% confident in feeling the difference between cranking the carriage of your machine and bumping into the face, noticing it, or chipping the insert. The second side of this part is just a straight turned diameter with no additional features apart from a narrow groove for a hose clamp. Drilling through the part from the second side, here you can truly see and appreciate the advantage of drilling with the carriage. It's no trouble at all to retract the tool as often as it is really necessary. Yeah, you can drill with the tailstock and loosen the tailstock clamp and retract the entire tailstock for deep hole drilling, but I found that to be rather inconsistent and inconvenient. Running the reamer through the entire part, this was a rather secret process. That's the reason why my arm is in the view of the camera constantly. But I'm basically just pecking my way through the part with the reamer. This is the retention feature for the hose clamp, using the same 1mm radius grooving tool that we used before for the thread relief. And I put a 6mm carbide chamfer mill into the bore of the part to give it a little bit more rigidity. This is just supporting the material against bending. We're going to do this with the horizontal spindle because then I can use the overarm support to, well, support my work. And I have a brass shim here, 0.1mm thick, because we're clamping on a finish machine diameter with a 3-jaw chuck, which puts a little bit more pressure per surface area onto the part compared to, for example, a 6-jaw. I'm comfortable clamping this with the 6-jaw later on the lathe to do some finishing work, but not to clamp it here with the hard jaws of the 3-jaw chuck. So I'm using the brass shim to protect the steel of this part here, especially since the 14404 stainless 316 stainless is fairly soft. So clamping it, we get our dial test indicator in. So I disengage the worm drive and I'm just free spinning, and I get a run out of, oh well, that's not brilliant. Let's see, let's zero it out. 40, 50 microns. Doesn't really matter, but if I get it to run through, I will sleep better. And I like to sleep well. So let's see, let's find a high spot. $50 over here. Okay, this is good enough. This will make me sleep very well. And what I did here, I just loosened the screws of the chuck and I shifted the entire chuck around on the flange. Very standard practice in my shop. This part is held on this thin diameter, and then it gets larger in diameter and cantilevers out basically due to the larger diameter, and I don't like that for machining the hex here. I'm definitely going to use the tailstock on this operation to take away any side loads. And that way I can take a fairly heavy cut without having to worry about vibrations, because the part is held in the chuck, supported with the dead center up here. I'm direct indexing in this case because it's very fast. I'm taking 2 passes, one time roughing away 2 millimeters of the material and then taking a 0.2 millimeter finishing cut. Running at 2000 RPM and a feed of 200 millimeters per minute, which comes down to a feed per tooth of 25 microns per tooth. Since we're cutting stainless, it's a good idea to brush on a little bit cutting oil. Okay, that was roughing at full width with this end mill. This is a 10 millimeter carbide end mill, and this left a rather nasty burr on both sides of the cut. So for the finishing pass, I will do 2 passes. So I will go this direction with the cutter or with the work elevated, and then I'm going back with the work dropped down. So I'm always cutting into solid material, and I'm left with almost no burr. Row on the MCO, and part goes in the 6th jaw chuck. I blew out the chuck so I'm sure there are no chips hanging onto the jaws. And also when I clamp it, I'm slightly rotating it back and forth to give me a feel if there is something wrong. And also I make sure that I take great attention on how the chuck tightens. If it feels somewhat squishy, there is something wrong with something between the jaws and the part. On a decent chuck that's not flexing, the torque curve of tightening it should be, it's getting a little bit tight, then it's just an abrupt spike in torque to a point where it's just bending and flexing that jaw chuck itself. Just like on a commercial nut that you purchase, we want to machine a nice chamfer onto the hex, and that's done by spinning it in a lathe. Well, in the case of commercial nuts, these are formed by a die, but we can do that on the lathe just by putting a 45-degree chamfer tool, chamfering it until we get a round surface that does not interfere with the side walls anymore. So there is a chamfer between the side surface and the top surface. Hard to explain. So this is too small of a chamfer. We still have a clear edge left here, so we go farther. And now we're almost there. We're almost in. We have almost a chamfer surface between side and top surface here. And how big do we make it? Well, so it looks nice. Should be the same on all 3 parts. Tiny bit more. Okay, that's a chamfer like on a nut. The only difference that the chamfer on the nut is formed, That's why it looks so super undefined. Also, it has a different angle. But we're going 45 here. And now we do the same on this side. Careful so we don't cut into the thread. If I had to do more than 3, I would write down my coordinates. Do it by DRL. Also, you can tell once you get a connected chip like this that you made the chamfer big enough. So that was the science of chamfering a hex. But Stefan, that's super simple. Well, yes and no. If you have never done it, might be complicated. So here's our chamfered hex. Now we're off to the bench deburring. Here at my place we use only the best of work holding for deburring on the bench. But I got a new toy. You have seen this before. This is an NSK Evo micromotor. It's just a Dremel that doesn't suck. So it has quick change for collet, 40,000 RPM. Super nice tool for rotary deburring. But NSK or Nakanishi also makes this thing. This uses the same motors. They make the motor in 25,000 RPM and 40,000. You can, they differ a little bit in their size, but you can tell from the color of the button. Blue one is the faster one, 40,000, and the green one is the 25,000 RPM motor. It has belt grinder attachment, well, finger sander or whatever you want to call it, and this is more or less a mold maker tool or a tool and die maker tool. Super quick belt change. Well, getting them off is easy, getting them on is a little bit tricky if you're clumsy. If you're a little bit more talented than me, it takes about 5 seconds. So here we go. Goes on like this. It's spring tensioned. You have a slack belt section for nice rounding, and you have a hard surface here for flat polishing. The belts are super cheap. They're like 20 cents or 40 cents a piece, euro cents. And they come in all sorts of grids. Adam the Machinist showed this previously here on YouTube, and I always knew that I want to get one, and finally I broke down. This is not a cheap tool, not by a stretch. It's horrendous expensive. You can get only the grinder head, it's about 600, and you get the motor too, which is another 700. If you only get the grinder head, you can change it just to your micromotor handpiece that you have maybe already. But that's an awful lot of screwing around, literally. So, very nice tool, runs off the same speed control. Tracks extremely well. So it's just a very nice tool. So let's deburr this part here. I made this wooden V-block here for bench use when I do deburring, so I can rest, for example, a piece apart in here and just manipulate it for using the belt grinder. You can hold it like a pencil like this, and then you just work on here. For the slack belt section, you can flip it over, hold it very similar, and use the rigid section. We want the rigid section for the flats to remove the machining marks, and the slack belt side to round over the edges of the hex. Okay, there we go. That's a super nice overall finish. No tooling marks left. All corners rounded, no danger of damaging yourself, and also very easy to clean. Back on the milling machine, adding the 45-degree cut to the end of the part. This is the side of the port that hangs down into the bioreactor, where the inserted media is dropping down. As you can see, the part is hanging out fairly wide from the chuck. So I'm taking light cuts and fast feed to keep the cutting forces low, so we don't get into trouble on this last machining operation. The brass shims between the chuck jaws and the hex on the part are there to protect the already finished surface, so we don't put any blemishes in it. Deburring the 45-degree cut with the belt grinder, just making it less an injection needle. Just rounding over all the corners and removing the machining marks. After all the deburring, hand blending and cleaning, the parts look like this. Nice and shiny, deburred, safe to touch, no burrs. Smooth surfaces all over that should be easy to clean. They look like a huge injection needle with the angled cut here, so you could just poke it in your hand. The angled cut is on there, so when a liquid runs through and you stop the liquid flow, it just builds a very defined droplet on the lowest point, and you can see when it stops dripping. So that's the reason for this angled cut here. I hope you enjoyed this little lathe and mill project. Thank you all for watching, and I'll be back.